In December last year, science teams at CERN's Large Hadron Collider reported a hint of evidence of a brand new particle, one that does not fit anywhere within the standard model of particle physics. If true, this would be the first clue of anything beyond the standard model from the LHC. Remember, the standard model is basically the periodic table of fundamental particles and forces that represents our entire current understanding of the building blocks of all matter. Even the incredible discovery of the Higgs boson in 2012 was a confirmation of the final particle of the standard model, and that was expected. If this is real, it may break open entirely new pathways to the research of the fundamentals of nature. So what was seen? Well, let's first think about how particle accelerators, and especially the LHC, work. The LHC occupies a 27-kilometre circumference circle beneath the Swiss-French border near Geneva. A ring of gigantic magnets accelerates protons to up to 0.9999999 of the speed of light before colliding them from opposite directions. The resulting collisions can produce temperatures of several trillion Kelvin. So, a tiny spot, for a tiny instant, resembles the state of the universe at a trillionth of a second after the Big Bang. Under these conditions, protons are obliterated. Their energy is released and reshapes itself into new particles. Many weird particles come out of such a collision, and some are so hopelessly unstable that they decay into high-energy light, gamma rays, before they ever reach a detector. We only know they ever existed because the resulting gamma radiation has an energy corresponding to the mass of the decayed particle. The Higgs boson was found because there was a slight excess in gamma ray flashes at 125 gigaelectron volts above the otherwise smooth spectrum of gamma ray energies. And now there's a new bump at 750 GeV. This suggests a new particle with a mass much larger than anything in the standard model. When it was first spotted, this gamma ray excess was just a little bump, and it could have been the natural result of random fluctuations. Those happen all the time. We wouldn't have heard anything about it except that two completely separate experiments using separate detectors, ATLAS and CMS, both saw the same bump. The significance of the result is still low, at around a sigma of 1.6 for CMS and lower for ATLAS. That's nowhere near the 5 sigma needed for a confident discovery. But particle physicists are completely losing their minds. Over 300 papers have been submitted to journals with a wide range of possible explanations. The broad family of possibilities include 1. Dark matter. There are theoretical ideas for particles that could cause a bump at this energy and would also make pretty decent dark matter candidates. 2. A gigantic neutrino. More accurately, a very massive cousin to the neutrino predicted by supersymmetry, and as yet unproven but pretty popular extension to the standard model. 3. The big brother to the Higgs boson, so a higher energy vibration in the Higgs field. 4. The graviton, a highly speculative particle responsible for the transmission of the gravitational force, but it's not yet even known whether such a particle exists or is needed to explain gravity. Or 5. It's a composite of other smaller particles. Just like the proton is a combination of 3 quarks, this could be a much more massive combination of several quarks and antiquarks. There are links to references to all of these possibilities in the description. There's no point choosing between these options until we verify the results. The LHC is currently offline for upgrades and starts up again in June, following a 2-week delay due to a weasel chewing through a power cable. I kid you not. At that point, the signal will either solidify or vanish, assuming no more attacks by cute animals. Okay, time for the solution to the dark energy challenge question. I'm just going to interrupt Matt here for a second. Sorry, Matt. He's about to go full nerd with the dark energy challenge answer.